I'm not your boss. Can suck in so many different ways. All right, how was everyone's weekend? Good. Okay. Almost everyone did their check-ins, so that's good. I graded some tests, so that's good. Only a couple people that I'm like not concerned about. I think everyone I'm a little concerned about. Some people I'm more concerned about. But that's okay, right? That's the point of like learning, is that generally speaking, you still start off by knowing everything, and then you work to get better at knowing all the things. So I've had conversations with some of you. I mean, a lot of the check-ins were very productive because we could kind of assess where people felt they were at and where they needed to go. You may see in the homework for this week that there are 2 problems in addition to the problem that I assigned from last week. There's 1 in 7, which basically asks you to verify that a certain E and B field satisfy Maxwell's equations. Right? You can't just write them arbitrarily. So that one is required. Then there's 2 more. There's 1 for like magnetostatics in matter, and 1 for electrostatics in matter, that I would encourage you to do, particularly if you feel like, oh shit, I'm really behind, and I want to demonstrate that I am doing good. Make sense? Okay, and if you were told that I wasn't concerned about you, good. So you don't have to do anything extra. Okay. Any questions before we start? Okay, so we're headed into the second third of this class, and it'll start with the discussion that we started with last Tuesday, which is essentially talking about how do we transport things like energy. So for example, currently you are seeing me. And if you're online, you are seeing me. How does that happen? So apparently I'm like gray and there is like a brown color. And this is all the function of your receptors in your eye. They are sensing photons of different energy. And those different energies allow us to perceive light. And so the biggest question is, how does light propagate with energy? Because we know that it happens like instantaneously for us, right? Lights go on, boom, right into our eye. But of course, we find out a little bit later that maybe there's a finite speed of light. And the question is, how do these feel, these weird things that we've been talking about, E and B, can they propagate energy? Of course, because we see, we know they do. Another question is, can they propagate momentum? We already found out that B does no work. So all of these things are sort of floating in our head. We're going to try and piece them together. Unfortunately, to do so, we'll have to relearn something called tensors. And we were really upset about that in fluid dynamics. We said, we hate these. We don't like stresses. We don't like pressures. And yet we're going to see them again. Okay? I know. You wanted to delete that, but you can't. All right. So, the first question, and I wrote something on the board last time. I know that was like 14 weeks ago, so you can't remember it. But we wrote something, and I said that there was a specific quantity, but then I like didn't give it a name. So we're gonna name that today. So let's write out some things first. Let's think about how we want to do the work. And I'll start it here. we talked about work with this, right? We said that work is the product of what two things? E and J, yeah, that's the end of it, but like at the very basic, that's where we're headed to, but right now.
Yeah.
Exactly right. So this will be the force over some little location like that, right? Remember that it's a dot product, so both of these are vector quantities. And how do we write the force? For anything happening in E and M, say a single particle.
Oh, QE plus B plus B.
QE plus V cross B, right?
Oh, yeah.
We're good. I see you. Okay. And what's another way to write DL that would be helpful here?
Oh, volume times not volume, velocity times change time.
Right. And this is helpful because we're going to use the fact that these two things are a dot product. So if I take the dot product of this and I'm trying to cross with the same object, boom, I'm going to get rid of terms. I love getting rid of terms. Right? Okay, so I'm going to take this thing here and I'm going to say that it really is V dot dt. Oops. Right? Okay, so then that will equal or another way of saying that is that dw dt is equal to q dot e. Are we okay with me switching the e and the v? That's legal. Okay. Okay, if we want work done in a volume, then we would say that this thing here is like rho d tau, right? And so you could integrate this entire thing, dw dt. We'd say that this is the integral in the volume of e dot rho v tau. And this thing here, this rho v, what's that? Rho v, what does the rho mean again? Charge density, and v is the velocity, not the volume. So it's the current, because it's the charge density multiplied by some rate of change. So it's the charge density per unit time per unit area, or charge per unit time per unit area, sorry. So this is J, by definition. Okay. So now we can make this particularly complicated. We said earlier that J, oh god, mu naught J could be written as del cross B minus mu naught epsilon naught ddt v. Okay. So I can plug that into here. And yes, it's upsetting. I know it's very upsetting. Okay, so we're gonna do that. Okay, we're gonna take this thing. We know that this is J. We're gonna divide by 1 over mu naught. It's gonna get rid of these ones here. Boom, boom. 1 over mu naught. Okay, and then this is gonna be equal to the volume integral of E dotted into 1 over mu naught del cross B minus epsilon naught. Super reasonable, right? There's a lot more fun steps, and the book shows them. Okay, but I'm just going to give you the result, and then we're going to interpret it much like we did with fluid dynamics. So thinking about how this E dots into this dEdt, you can do the chain rules. You can look at how these are related to each other, and you can collect like terms. I encourage you, I think it's page 46. Reasonable. It's like half a page, but it's just a lot more dot products than anyone gives a shit about. Okay. And instead, this is the result. And that's pieces that you might understand. Minus. Okay. So you're looking at this and you're thinking to yourself, that looks like garbage, right? It doesn't have any sort of meaning to me at all. Well, in fact, it does. And you can remember what some of these different pieces mean. What was E squared? Work. Right? Or energy. And what's V squared? Probably also work. Also work. Yeah, we're talking about work. So it'd be really good if all these things equaled works, right? Okay, so what does this first piece mean?
Looks like the change in work with respect to time.
Right. Okay. This piece means change, the rate of change. Okay. So this thing is saying that the work that occurs is due to the negative work or the negative rate of change of this something. So now can we understand what that something means?
The potential.
The energy stored.
The energy stored in the field. So this says the work changes because of the energy stored in the field in a volume changing. Good, that one's sensible, right? Okay, so we look at a box. We're currently in a box. We want to know how many people are in the box. Well, we can see how many people came and went by looking at the difference in time between how many people, let's say all the people of different types are in the box, all in short. Make sense? Okay, so that's the first piece. That one's super sensible, right? Okay, and then there's the fun one. The one that we didn't discuss last time. What's this?
I'm gonna take a shot in regards to current.
Why?
It has, because it's an electric field crossing the. So
Why is that occurring?
typically, when you have like the current, then it creates a magnetic field. And then like it could also possibly be inside of an electric field. So I'm thinking like when I see E and B together, then there's probably also a current somewhere.
Okay, okay. I like it. I like the thinky thoughts,
Yeah.
but no, dang it. This one is more abstract.
Okay.
Okay, and the hint is not really in these two. I mean, this is certainly a hint, but like you don't know what these mean yet. E cross B doesn't have that intuitive feeling that something like E squared, which looks like V squared, which looks like 1/2 V squared, which is like work, right? This one here, I mean, I don't know that you have that intuitive feeling yet, right? But this thing you might.
I'm thinking like a flux.
a flux.
How much stuff can move through the area, because you're not saying how much you can move through.
Right, yeah, this piece is coming along for the ride, but you're certainly right that you think about this thing as having an area. So let's say we're thinking of the box again. My ability to pass through this door, right, is the flux that I'm considering. So what this says is the total work done, or the rate of change of work, is due to the rate of change of the energy in the fields and the flux of fields going through the surface. So if, for example, you have a box, okay, and an equal amount of energy comes in as goes out, then this is not going to change, and this is going to disappear, right? Okay. This thing is called. One of these is good. Yeah, that's fine. Okay. So let's write these out really quickly. So this here is the decrease in the stored energy. Different from just E, electric field. And as we pointed out, this is minus the energy that flowed in or out of the surface. Okay. This is the work done by charges. I didn't mention that. Okay. And this whole thing gets the fun name Poynting theorem. It's Poynting. That's me pointing. No, there's nothing there. Okay. All right. So what this basically indicates is that fields can transport energy. So this is the section that says there is a flux. And essentially what this is telling us is that E cross B has the ability to carry energy. Okay. And it gives us our new favorite vector, S. All right, so what's this called? Right, so you'd assume that S would mean something to do with S, right?
Yeah.
But of course it doesn't. This is Poynting's vector. So Poynting's, okay? It's not gonna be easy to remember, but it is the weirdest one, right? Okay. All right, so this is essentially, this is Poynting vectors, and this is basically telling you the energy flux density. A compactor version of writing this piece here would be okay. So now I've said the same thing, but with a lot less letters. So the mechanical work that's done by charges is due to the rate of change of the electric fields and magnetic fields, or more left, I should say, any energy that's carried by the fields themselves.
So would it not help for us to picture E cross B as like vectors that create an S vector, or like what's the meaning behind the cross? Okay. Okay.
So, let's use a right hand rule. Okay, so this is E going up this way. This is B going that way. Which way does the energy flux go? E goes this way, B goes that way. Energy flux goes that way. So if you have E and B perpendicular to one another, you can propagate energy. What if E goes this way and B goes this way? No energy can be transported. In practice, that doesn't happen. Okay. So when a field does work on a charge, it increases the mechanical energy by the same amount that is lost by the field. Let's think about that for a few seconds. Okay, you have a wave, or you have some form of electromagnetic field that's interacting with the particle, with charge. Okay, then we accelerate that particle with charge. It gains kinetic energy, and therefore the total energy in that field goes down. That's reasonable. Okay. Is that reasonable? Okay. Is that weird?
So it's collecting energy from the field itself. That's how it transfers.
I want you to think really quickly about an analogy. This will make you uncomfortable. Okay. There's a ball on a hill. The ball starts rolling downhill.
Does the hill get smaller?
What's the question?
I guess so. In this case, right?
Well, the potential energy, remember, is a product of both of their masses.
Okay.
Do their masses change? No.
Okay.
No. What changes?
I don't know. I guess it's energy state.
Separation.
Okay.
One got closer to the other. Oh, phew. Okay, energy was still conserved, right? Okay, but you just might go down a little rabbit hole and be like, well, this is so weird. No, it's perfectly fine. We think about this in the context of gravitational potential energy because that's what we're more comfortable. We're used to balls rolling down hills. Okay, the only thing that's happening here is that sometimes you go in a spiral corkscrew helical path and it doesn't look normal, but it is very natural. E and B is natural. Everyone has E. Okay. All right. Let's look at this piece here. So we said that, we said that. I'm gonna write a few things, then we'll do an example. So just to make sure that our brains are awake. Okay. So you can write this as this is the lowercase u for energy density, not the total energy. And you could write this as well. So this conversion, this step from here to here. Gauss's theorem. Allows us to write the sources and sinks as fluxes through a surface, and divergences as fluxes through a surface. Okay. Or another way you can write this piece here, just cleaning this up. So we see the integral on this side, we see the integral on that side. So we want to just ignore those integral signs. And we're just going to take this piece here and take this piece E ut of the, oh gosh. Minus as. Oh, I dropped it. Yeah. Okay, what am I saying here? This is the flow of energy. Okay. So I'm saying the change in the energy in the field and the mechanical energy is equal to the divergence of the Poynting flux. So another way to state that is that if I have no Poynting flux, okay, then these can only pass between each other and they won't change in total. I can't get flux into the system without the Poynting vector. Okay. And another way to write this thing here, since these are little u's, not the big U, capital U, you can write this as big U. No. Like that. Okay. Wait. Oh, sorry. This is the analogy that I was trying to make. So here you have the energy equation talking about how the rate of change of energy in an area or volume is going between the field and the mechanical energy of the particles due to the presence of Poynting flux. Similarly here, the rate of change of charged particles in some box or some area in the same way that we do about this room. So if we want to change the charge in here, someone has to leave or arrive. Okay. If we want to change the total energy per unit volume, then some light has to be. I didn't say light. You don't know about light yet.
Oh, got it.
Okay. Okay, people upset about that? Okay, let's use our brains for a little bit. I know that we don't really like doing that sometimes. It's morning. I didn't even get enough coffee. Coffee that I got was super watered down and I was upset. I need this more for me than I think you do.
Copy.
No, this problem we're gonna
Oh,
okay. Okay, but you're the lucky ones because this is the homework problem. So lucky. Well, there's folks who aren't here. They're gonna be very upset about the fact that they're not here. Okay. So this first one is we're gonna imagine a cable. And this will be 8.1 in your textbook. If you want to look at the picture in there, might be a little better than I will. But we're gonna try it together. These are the worst choice.
Yeah.
But like, this is what they leave me.
All these big ones, these people scroll on.
I know, but do I want this one? It's like, I know I'm gonna break it.
You could break it now so that way you don't break it later.
Okay, you're right.
They do the perfect sense.
I'm
Yeah.
using-
Nice.
Wow.
Nice.
Sounds good.
All right, you guys know you haven't got your test back. That's the one that really needs to me. Okay. All right, how far am I still in the picture here? All right, here's 8.1. Okay. So essentially, you have a concentric cylinders. We've seen this set up a bunch of times. We're getting tired of it because money. Okay. So on the outside is I moving to the left, and on the inside is I moving to the right. Okay. You have two surface currents. These are conductors. So both of them are conducting, and they're at a potential difference of V. So okay. what is the energy per unit time transported down the cable? Oh, that's not even. What is the E over T, so this is energy. Unit time, we call this power. Transported down the cable. Okay, so I love that you're already going to the thing that we just used, right? Because we're thinking to ourselves, well, it's gotta be fucking relevant, right? Someone's gotta use it. So let's fucking hope, right? Let's have a look at the units really quickly. Because, we don't, I said we're gonna talk about S as this weird thing. Do we have, some basic understanding of what the units of the pointing vector are here? No, good, that's very right. This is a weird looking thing. Let's look over here. So this is what? This is a power. So this has to be, and this has to be? Good. So now what is the units of S?
Oh, joules?
No, don't do that to me. How dare you ever use SI units near me? That's not what this class or country is about, okay?
Wait. Power times meter squared.
Why are you using, you just tell me what meter squared is then? Area, okay, area, volume, I don't care about meters. No, because that hurts my soul, right? I'm an American who loves yards. I only wanna hear about them in inches per square inch. I'm just kidding, yeah. Okay, so this piece here, in fact, is not what you said. The whole thing is a power, but the S is, hold on. Say that again,
Why were else send it?
what'd you say?
It was just like not area, it's just no area.
I said how
Power over area, because then we multiply it by area to get a power.
Yeah,
Good. Okay, we all knew that, Krismani. Quiet. Okay, so this is energy per unit time per unit area. What?
You just do times here.
That's legal.
yeah, that's allowed.
You can do this in any country. You can do this. This is permitted.
If that was like 10, and you divide it by 2,
Oh,
and then by
so
5.
sorry.
Okay, so I want you to spend 2 seconds, 5 minutes or so, thinking about the problem, thinking about how you would attack the problem. And we are gonna do this as a group, and then in 5 minutes, you find your friend, you see what they've done, you investigate it together, okay? And engage with the content.
Okay.
Why don't you find a friend and ask them what they're. If you have reasonable needs. You may have to move. Oh, sorry, yeah, that was okay.
What were you thinking?
Hanging in there.
Yeah. Okay, so I got this far.
Yeah.
It's supposed to be soon.
This is like the start of what I think we can be. I also know that we're probably gonna have to be looking at it in terms of like the inner cylinder and then the outer cylinder. So this might be also broken apart in like
Yeah.
two things where it's like, oh, okay, what if this was like equal to this A radius, and then another situation where it'll like add that's what I'm thinking, yeah. And then we can think about how they interact together. But I think we're using Gauss's theorem. Might also have to think about. This is just the area. This is. It's like something else that we have to reason that, because if we can find as, then it's a matter of by, or no, I guess multiplying it by area. Yeah. So we're thinking about this guy. Yeah. Trying to think of like what E would look like. You have eyes, and then B would be wrapped around your sister. But I think that's something we can look at actually. Say, oh, what is magnetic field on the cylinder with currents going? I think that's like a start, and then we also, you know, what E would look like. And E, I think is perpendicular to your surface of the cylinder. Yeah, so you'll have to look at it like, so there's like an E, there's an E in the inside cylinder, or an E coming out the inside cylinder. And then a B that's going around top end. Yeah, and then there's a bigger one. Yeah.
Wait, so do you want the power like in the G?
Yeah.
You done?
Yeah.
Good. Anyone else done?
Thinking about it.
Where does it want to get the power? Wouldn't it vary?
Yeah.
Like where we actually do our. Infusion.
You probably put both.
But if you put both currents, then I frame closes to the theory. Opposite direction.
But they're over different surface areas.
But like if you have a big enough. Absolutely everything.
They're over different surface areas. And
Okay, this is a great discussion. We're gonna pick up on this. How you guys doing?
I know it has to do with their boundaries.
Okay, and those folks in the back who don't talk and just. I mean, are you fighting or arguing?
Yes,
Oh, you're agreeing?
Yeah.
That's how, oh no. Okay, so you guys got it then.
Nailed it.
You nailed it.
First try.
So, yeah, so let's see it then, right? Let's see it. Okay, I'm not gonna fuck people's morning up that badly. So let's think about this from the perspective, of what do we need to know and how do we get there? Right, because that's always the hardest part. We have all these pieces flying around. Okay, so instead of everyone shouting at once, okay, you're pointing at this piece,
No.
No.
I wanna find E
this piece. You wanna find E.
and B
Oh, E and B
and cross them.
and cross them. That sounds like a great plan.
Yeah.
But I know that because I know this. This is what I was asked for. I wasn't asked for that. So I'm going one step backwards to demonstrate that I know that this here, this W dt, that's power. And I see this thing. And I'm like, oh, if I can do that thing, then I can probably do this thing. Right? So that's just one more step. Okay, so you want this, and you're like E and B. Okay, now what do you do, John?
I was thinking about how it would look like on each, I guess each cylinder, like what E would look like and what B would look like.
Okay.
On like one of the boundary conditions, so it'd be like the inner cylinder and then there's the outer cylinder. That's where I got, but I was still thinking about what that would look like.
Okay. So what do you have? What's your next step?
We were just kind of the same thing, just finding E and B. I kind of think you already said this on that for a second.
That's okay, that's okay. So he was talking about, finding E at the boundary conditions,
Oh, okay.
right? And I think you guys had this discussion too, or y'all had this discussion, you were like, where is P? Where is E?
We thought it was in between the two cylinders.
Okay, so you have a vote for in between the two cylinders?
Yeah.
Anyone have a vote for everywhere?
You just vote for currents, whoever wants to use them.
Right. So you're thinking to yourself, they gave us both currents, they probably want us to use both. But let's think about, if we were just doing the E of this problem. Let's forget about all the extra garbage, right? There's no dielectrics, it's straightforward. So let's just look at E. Okay. I have a changing, or I have an I that's going into the board. I have moving currents, right? Maybe the easier one to think about would be B. If you're in these different regions, right? This is how we like to split this problem up. You might do something like, this is region 1, this is region 2, and this is region 3. So what is the magnetic field in region 1? 0. Because there's no current enclosed, right? Ooh. What about in 3? Boo, no current enclosed. So now, if I look at my S, okay, I don't even care what E is. Because in regions 3 and 1, S has to be 0 because B is 0. Alright, so you just get that for free. So now, so now all you care about is in region 2. Is that solvable?
Yeah.
Just one I, yeah, it's pretty straightforward. So now I can calculate E and I can calculate E. Now what are those? It's like first cylinder. Which one is that? E equals? Correct? that right?
Mm-hmm.
Okay. Which direction is it going? What, R hat? Phi hat? S hat? Well, you tell, okay, you're all shouting at me now? This way. Okay, so we're going, wait, this way? This way.
Yeah.
So we're gonna choose, we're gonna make some choices. We're gonna say that's what, Z maybe? And that'll be S. And now I've defined phi. So maybe that helps, right? So I'll do something like this. V. R. Or S, which one do you want?
S it is, because it's more confusing.
Yeah, because we're not gonna use a different S later, right? That will be perfectly normal. Oh, God.
They can all say X.
Just everyone who's not here starts crying. Okay, so this is fine, right? We like that. And so then this is in the direction phi. That's the claim. Uh-oh, now what do I do about E? Possible, right?
Yeah.
Oh, let's think about what it means. What does it mean, I?
So charge time.
Charge per time?
So, yeah.
Sure, that's one way to think about it. What? Yeah, something with velocity, right? Now, if I want to have it, you're correct in the units, right? Charge per time. So if I wanted something with velocity, I have to do something with that charge. Let me say this differently.
Yeah.
Ready? Okay, here's I. I
Divided by distance.
has units of Q per T. And I want to jam a V into there.
So you gotta also like divide it by a distance.
Okay, so I like that. So I'm gonna say something like I is equal to Q over L.
Sure.
For length. And I'm gonna times it by L over T. And I'm gonna say these are equivalent. Because this one I like, that's called my V. Even though y'all hate the way that I do my V. And what's this one? I know that looks bad too.
Oh, that's your surface,
Lambda.
there you go. Yeah.
Okay, so now I know what lambda is. I equals lambda V. Or another way to write that is lambda equals okay. Can I catch the E? We'll see it there, right?
Very close. Don't we know that E is supposed to be like normal to whatever surface we're looking at? When for like a cylinder, like when we're thinking about geometry, that
Okay, so we're thinking about, we've done this problem before. We
yeah,
have some charge on some cylinder.
yeah,
And even though the charge is moving, and any snapshot that we take in our mind, we think of it as not.
Yeah.
Right? Okay, so then we look at this cylinder. It's got charge on it, and you said, well, it should be radial. Okay. That's the claim. But reasonable? What do you find?
Gauss's law.
Yeah, you can do Gauss's law. And what's the answer?
Yes.
No, you just find it in the book.
Oh, okay.
It's in chapter 3.
Oh, yeah, that's why it's like the inflatable water.
Over to I have some.
Very close, but I'm gonna use a different letter than you.
X. Okay. You need,
Yeah. Then the question is, what's the variable? What did you say?
S.
Where? Is it here?
On bottom.
On the bottom. So I'm gonna do it like this. Okay. You like that? And which direction does it go?
Yeah, so, yes.
As that?
Yeah.
We like it or no?
We love it.
Hands up for S hat. Wow, that's unanimous.
Wow, everyone's wrong.
Okay, all right, so now here's the big reveal, right? This is what everyone's been so interested in, they're so excited. They're like, do wires transport energy?
Yes.
Oh, I hope so, because this cross run is gonna work. Let's have a look. Does B cross with E?
Yes.
Yeah.
You can, yes.
Let's go.
Yeah.
Let's go.
It makes it see.
Yeah, okay, so let's think about this, right? So E is crossing with B, so S is crossing with phi. How does that look? Z hat.
Sorry, I'm
Let's
trying to get this right.
S. Oh, okay. What? This is our passage. Okay. I'm just kidding. All right. So let's think about how this is done in practice. Let's put these pieces in. Okay. So S is 1 over mu naught. Okay, and let's do the E piece first. Lambda over 2 pi epsilon naught 1 over S. Okay, S hat crossed with mu naught I over 2 pi S pi.
Done.
Is that okay?
And then just times it by an area.
So what does that actually equal? Let's do this one first.
Yeah. Done.
And pull out all of our constants.
Yeah, like the.
Replace lambda with
pi. Oh, do you wanna do that way?
No. Let's not overcomplicate it. Everyone has to get E's and. Let's leave things as they are, okay? Let's do 4 pi squared. Epsilon naught. Also gonna do lambda, or lambda. And then I have 1 over S squared. Okay, and then I have S hat cross phi hat. And this is. You gotta shout, otherwise I can't do. Okay.
So,
That good?
you're
So
fine.
S.
Like rows.
No, they don't.
They said it would be-
It kinda hurts sometimes.
Your bees.
It's like when you're speaking a language, right? You're like, what does that word mean? And I know from context. I don't want to though. You want it like this?
Like a
circle or
Yeah, draw a circle.
You're like so close to that circle.
You want this?
Yeah.
Yes.
Yeah.
That's not a phi.
That's so clean.
That's a capital phi.
That's good.
That's.
You have this too. You want that one?
Oh,
That's also a different one. Right. You want this one?
usually people want zero job.
That's a row.
That's funny.
Alright. Okay, in practice, when I'm writing rows, and you can see it here. Oh, yeah, now. It doesn't go up at the end.
Yeah.
Oh, okay.
That's the major difference.
That's the distinction.
That's the only distinction. Okay, here's U, and here's V.
Yeah.
See the difference? See the hat?
I think you could differentiate capital U and little U has like the little tail and then U is just like a.
Just explicitly.
Yeah,
spell
this is
that out.
big U.
Just be like phi.
No,
Okay.
just without the tail, without the tail. But then you can get it, the difference. Just give me,
This is differentiable.
not
No,
the,
no.
not the little U.
See what the, no, the little U and the big U, just this one has a little U.
That's like an L, but.
So a little U, I do this, and I just write straight down. A big
L,
U.
Okay. You didn't do that there though.
Where?
You did. You
It's
did.
fine.
It's literally right there. You have to get close.
It is, oh, I hate that.
You right? I see it. Alright, calm down. Alright. No revolting in this classroom. Keep your pitchforks to yourself. So are we done?
No, we gotta make it, yeah.
We're not done.
Area. Integral.
Okay, area integral thing, good, so it's not just times an area. Right, so we need to think about what we're doing here. What is the area?
The cylinder.
The area of
Circle?
the experience that
Or is it sort of?
I thought it was surface area, it's like an enclosed area.
So let's think about what we physically mean here. The question we're asking is how much energy or how much power is transported by this configuration. So which direction is the power?
Oh,
Z.
it's in the Z, okay.
Okay, so we would want the flux to be perpendicular to what surface?
Yeah, the circle, like the cross section of the cylinder.
True.
Yeah.
So let's say I do something like this. I make a really big circle. Okay,
Still a circle.
sure. But it's in the Z, or it's in the R, right, phi plane.
Yeah.
Okay, and it can be anywhere, I don't care, I'm just taking a cross section. So my first question is, what is the power here?
Zero.
Good.
What is the power here?
Zero.
Good. So really all I want is this hemisphere. Right, this semicircle. Right? Ooh, okay, so what's power? Power is the integral, the surface integral of S dotted dA. And it's really important that we figure this out properly. It's not an Amperian loop. It's not a Gaussian loop. It's the one that is appropriate to the surface you're going through. So Z has a specific direction. It happens to be aligned with, sorry, P has a specific direction. S has a specific direction. It happens to be aligned with Z. That may not be the case. So if, for example, these ones had maybe more than one component, say a radio component and an azimuthal component, or maybe one of them had a little bit in Z, then S could be going off to the side.
Yep.
Right? Yeah, disgusting. But how would we construct the surface? Well, we would want one that accommodates for how much is going through that surface. Because ideally, we can construct our surfaces such that they are tangent or perpendicular to the incoming S. Right? Because if we construct them so that they are tangent to them, that's pretty silly to get zero. Right?
Would it be like an oval or a rectangle? Like so it's like something like that.
I mean, okay, here's an example. So you have this S going down along Z. How do you construct a surface so that you get the wrong answer? Yeah, exactly. Right. So maybe I make a nice little wafer thin slice and I place it so that its axis is oriented along Z. Right? Now I've done all the right steps, and then I did the last one wrong. And I get P. Obviously untrue. Okay, so in practice, what does this integral become?
Circle.
And more? What do we mean by this? How do I write this integral? Very good. And so it's a double integral because it's a two-dimensional,
Yeah.
right? Okay. And I'm gonna write just S in here right now. I'm gonna fix that later. What did you say? TS5?
Yeah.
This is big S. Okay, what's the last piece here? What am I missing? What? Exactly right. So what are they? Okay, does it matter where? No. You said nah. Nah.
Zero and X. The radius. inner
Whatever you choose, yeah.
That's-
Oh,
Yeah, so let's call this inner radius A,
A.
very smart, and then the outer radius,
B for
that
bigger.
A for smaller, smaller, and then B for bigger. Good. All right, now we're done, right? Okay, so you can do that integral. You will find out that Oh, you also are
B
gonna.
minus A squared. or something.
Yeah.
So-
Like an S or something.
Yeah, there's a scale factor. So when we're thinking about the fact that this is, two lengths here. And you'll see this when you think about this, right? So this is ds, that is given in terms of meters. Right, and d phi is given in terms of radians. So it's really not d phi, it's what?
SD5, okay.
Okay.
All those S's.
Yeah, it doesn't look good. It doesn't look good, but it simplifies. Okay, let's do it together.
Do we just leave the S factor alone right now?
I think it cancels out with 1 over S squared.
I mean, we have this stuff up here, right?
Yeah. Oh, okay, yeah, you just grab 1 over S squared.
Okay,
So
you tell me.
is it simplified to 1 over S?
Yeah.
Yeah. And then just all that. Oh, yeah. Yes.
Okay. So what's that? Natural log of this.
Yeah,
And specifically?
B minus C.
I over 2 pi epsilon.
Yeah, but for the integration.
E over-
Very good. All right, so we can write this as lambda I over
2 pi epsilon.
job. LM.
That's it, like, we put this on our homework and we get an A.
No, you still have to, you still have to get like the. What is it, the change in time of the U. What,
Yeah, what was B?
Yeah, cause that's just
Oh,
the
yeah.
pointing, right?
let's just ignore that.
Okay. So. I like the enthusiasm. The power is, of course, I V. And P equals IV. Do you remember that from?
Wait, I thought power is equal to I squared.
Yeah,
Yeah,
you could-
negative, okay.
yeah,
Okay. So if you calculate V equals E dot DL. okay, you also get this. They are equivalent. So you're done here. And you're saying to yourself, that's not, like, what about these other terms? Well, the first question is this one?
Is it changing? No.
Not changing. So you're absolutely right, right? We have to check all 3 terms. The first term is just not changing. It's in steady state. There is power, because it is changing mechanically. Okay, do we love it?
load that.
Do we love it?
Oh,
It's reasonable, right? It's not so mind bendy as it was before. We're just taking stuff that we have and we're crossing it into other stuff, and then we're like massaging it together. It's okay. Okay. There's not another example, but I'm not gonna do it for you. Instead, I'm gonna give you a conundrum. So ready to get conundrums. All right. I love the enthusiasm for getting confused, right? Because this is gonna lead to a really interesting question. Okay. We can imagine 2 particles. And let's assume that they are both electrons. And let's place one here. And it's gonna be called Q2. We're gonna place one here. And it's gonna be called Q1. Okay. And what's their electric force between them?
Like the whole thing.
What's up?
The 2 cubes on top and then like some freeze at the bottom.
Yeah, I don't care about that.
okay.
Just generally speaking, point and tell me, right? Like hand wavy. Good, yes, they're there. Okay, interesting. So
Oh,
they're
yeah,
both,
sorry.
Either that or,
well, which one?
Well,
we gotta know the.
I told you already.
Electrons.
They're electrons.
Oh, okay, then they're.
Okay, so electrons are not friends. They don't want to hang out together.
Oh, no, electrons go away from each other.
Okay,
They're
okay.
both- yeah. Yeah, it might flow together, but not getting along.
Yeah.
Okay, we like it yet?
Yeah.
Okay, everyone show with the hands. So with it. Hey. Okay.
I was thinking that way.
Okay, so this is the force of 1 on 2, and this is the force of 2 on 1. And there I can very easily see that F12 equals negative F21. Is that correct? Good. Let's assume they are moving. Okay, so this is the velocity of 1, and this is the velocity of 2. All right, so now I would like for you to draw on your little draw. The force direction for this one or this one. You choose one, and then we'll put them on the board.
First direction of. Like the net force on one?
No, we're just gonna do the magnetic force now. So this is a charge moving, so it's going to generate something, blah, 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 right?
So the closer they get, the more they go this way, but if farther they are up here, then this is gonna be like.
Are we assuming like your constant?
Yeah, we're assuming constant velocity. I just want to know what each of the forces looks, what direction each force looks like. Okay. So the force here, I can show you, the force of 1 from 2 is in that direction. Here, the force from 2 on 1, sorry, the force on 2 from 1 is in that direction. This is just the electric force. So let me just qualify this with E. Okay. And now I would like to know the question, F of 1 on 2 M. Question mark? And similarly, for the other one. Is it no? It's deep knowledge that's unattainable. Does anyone have one of them? Okay, what's your guess?
If the bottom one, the magnetic field should be going like into the board on top of it, so maybe it'll make the other one go into the board.
Okay, so I like that argument. So you're saying, let's imagine that that QV is like an eye. Right? And so therefore, I'm gonna follow it around with my right hand. And so it's gonna be in that way. And similarly, this one here.
It comes out on the, like,
Okay, so it comes out on this side. So it's maybe impacting this side out. Okay, so let's assume that that's correct. Right? No, that's a good assumption, but let's investigate what it looks like. Okay. So this one here, what is the force of B from that one? So V, which direction was it again?
Yeah.
Where's B again? For the one on the bottom?
Negative X
It's-
direction. Like this.
I need to know in or out of the board.
Oh, I'm sorry.
For the bottom,
Oh,
where my hand is.
oh, it'll be out.
it'll be out of the board.
Yeah.
Okay, so V cross B. Is that correct?
Mhm.
So V cross B, and the force now
Is up.
we're claiming is up. All right. This is F 1, 2, V. All right, this one. So this one is going down.
Is that the force it does on itself?
No. This is the force on 1 from 2.
How did you get that?
So here I said the magnetic force, right? Remember that F from E is simply QE. And the F from B is Q V cross V. Right? So I'm treating them like point particles, I'm giving some approximate by V fields, right? We're not calculating these specific, I just want to look at directions, because I think there's something that's going to be very unsettled. Okay, so this one's fine. This one here, we're going down. And which way is B? B is into the board.
Oh, yeah, from that's me.
Yeah, so on this guy right here.
It's
B,
going right. Is that what it is?
And if you're saying you want to find the magnetic force from this magnetic force on that one, then why don't you use that magnetic beam?
you are. So here's the magnetic field, like you said, right?
Yeah.
So it's into the board for this one. So maybe we'll write that right here.
Like what it's been experiencing.
Yeah, so this would be B from 1. Is that what you're saying? And then this one here. Okay,
Yeah.
set it down. So it's actually out towards us here. This is B2. So now that cross product makes perfect sense, right? B, F.
Oh, okay.
And this one here, V. Gotta orient my fingers properly. Okay. B, F. Is that correct? B.
Yeah.
B. Oh, that way. Okay, all right, I did it wrong.
Okay.
All right, so it's this way. So it's B, F.
Nice.
Okay, cool. Okay, and our conundrum presents itself.
How do we have
It's on there.
What? It's a lot of work, is that what you said?
It's like what happens if they, like, if they ever collide?
Is F21B equal to F12B?
Of course, in magnitude only.
Right, question is, are they equal and opposite?
if they're moving at the same rate?
If they're correctly,
You tell me, look at the direction of those forces. Yes. How is that possible? I'll give you the hint, it's not possible. So even though we calculated the forces correctly, they are not equal and opposite. So if you think that we just broke Newton's third law, that's what you have to come to class for on Thursday. There's a clever way out of this, but you're not gonna see it just saying, have to like math it. It's gonna suck.
It's gonna be like you dumb term have that.
Hey, okay. Everyone unhappy? That's ideal. That's the, I mean, you gotta stay engaged. You gotta stay, you know, like I'm ready to go.
You gotta feel sick.
And right now we're on number 8.
Yeah.
If you did the exam, and you want to turn it any updates, I'm perfectly okay with that. However, if you, forgot. If you want to turn in any updates, I'm perfectly okay with that. If you don't, and you're just happy with the feedback you got, and you want to demonstrate to me that you understand what you did, just do those 2 problems that I assigned. They will be extra credit for anyone that I didn't say I'm concerned about.
Alright.
Makes sense?